So in this recording, in this video, I'm going to talk a little bit more about the details of the machine state that we're in when our Uefi application actually starts up. So the Uefi standards has a fair amount of things to say about that. I'm going to look into what they are and how we can actually test them and see that they are indeed what they are supposed to be. I've also been, thankfully, lots of great comments and feedback from the last video. Really grateful for that because it helped me clean up some code and figure out how to do things better in Zig, which is of course part of the reason I'm doing this in the first place, because I really like this language. I really like to use it. I find it, even though I'm a absolute novice at it, I find it incredibly intuitive and really easy to reason about. Yeah, I think I'm gonna want to do a lot with this, a lot more with Zig. So one of the things that I did the last time, and it was pointed out to me, was I had this slightly clunky conversion of UTF-8 strings into UTF-16. So the UEFI console print functions, you can see, the stuff I'm calling here, they expect you to pass it a UTF-16 string. That's just part of the standard, that's what they do. So what I thought, since the string literals in Zig are UTF-8, was that I had to convert them to UTF-16, and I had this little conversion function here, very simple. All it does is it takes the input, which is UTF-8, 8-bit, and it casts it quite simply to 16-bit, as you can see here, pretty straightforward. That's obviously not the right way to convert UTF-8 to UTF-16, but it works as long as your characters stay within ASCII range, which they do. And I did that so that I could then call things like buff print, so I can do formatting and create a nice looking output, or just print stuff in general. It turns out you don't have to do that. Thankfully, there is this thing here, which is the UTF-8 to UTF-16 LE string literal in standard.unicode. Which means I can write the string literals like this, which is really cool. And I'm assuming, I haven't looked at the actual code, but I do expect that these are, since they are compile time known, that they will be handled by the compiler, and there's not really any, it's probably zero runtime overhead of that. So that's great. So that simplifies my code a lot. So I split things up a bit. I've created a few more modules that I'm importing, utils, which still has some of that UTF stuff, some system info, which I'll go into, and the kernel.zig file. So what I'm doing now with this version is I'm just printing out some more information, and I'm going to run it, and so you can see what it does. Okay. Boom. Doesn't say much, right? It says paging is enabled, PAE, a physical address extension is enabled, long mode is enabled, and we are executing a long mode enabled code segment and then going to sleep. And that's all it does for the time being. But all of this is kind of interesting information to find out anyway. So I'm going to go to dump system information, which is the function that does all the magic. By the way, that's popping up and reminds me that I installed the Zig language runtime, the Zig language runtime for VS Code, which is really useful, super useful. So if you're using VS Code for this, absolutely get ZLS. It's easy to say CSL for some reason. Anyway, there you go. Right, so let's go in here. So this is the function that is going to test that what the Uefi manual standard says is indeed what we are served. So it says basically that there's a prescribed execution environment. When you are started up, when the firmware has loaded you up, the execution environment shall be, here comes the list. You will be in single processor mode, so you will be running on the boot processor. The boot processor, of course, is an arbitrary core that's picked, an arbitrary processor that's picked by the firmware when it starts up. Any other processors you have, any other cores are idle. They will later on become the APs, application processors, but they're not initialized. They're not running. There is no code running on them. They're not ready yet. So we know that. I'm not going to test that here. That's for a later video. We're just going to assume that that is correct. We are in protected mode. So we are in the mode where you have protection levels, privilege levels on segments, so that you can run in kernel, ring 0, 1, 2, 3, etc. Paging mode may be enabled. It's sort of interesting that it says maybe. I suppose in some ways, I was sort of trying to think, well, would you switch into protected mode without any paging? Not really sure that makes a lot of sense. But if paging mode is enabled, as it says here, they recommend that you have physical address extensions enabled, which means that your page table basically has a little bit of extra depth to it, which means you can address bigger memory spaces. And also importantly, what it says here is if paging mode is enabled, then the Uefi memory map is identity mapped. So that means that a virtual address is equivalent to a physical address, and there's still a lookup, there's still a virtual address. Go into the page table or page directory, find the page table entry, and get the physical address from that. But the physical address you get out of the other end will be exactly the same as the virtual address. And that's a very, very common thing to do for the sort of early stages of an OS or kernel that's loading up, is that you identity map a portion of memory. Usually if you're writing old BIOS code, or code that is running in an old BIOS environment, then you usually identity map the first megabyte of memory, so that you can access things like video RAM, and there are reserved regions for particular uses in that first megabyte, and you can access them using just the physical addresses, quote unquote, because they're identity mapped. So that's a common thing to do, and that's why it's also called out here that that's what's done with the UEFI memory layout as well. Interrupts are enabled. Okay, that's fine. Direction flag is clear. That seems to be a sort of thing that you always do that, right? If you write your own bootloader, the first instruction probably you put in there is CLD. It's a thing. It's a ritual, a rite of passage. Undefined, yeah, that's fine. We have 128 kilobytes or more of available stack space. That's wonderful. It's 16-byte aligned. Here comes some stuff about the floating point control word, multimedia extensions, and CR0 control register 0 EM emulation flag must be switched off, and CR0 TS must be switched off. They have to do with the fact that if x87 instructions, so the old floating point coprocessor instruction set that Intel produced a million years ago, they can be emulated. They can actually be emulated by IA32 architecture. And so if you try to execute one of those instructions when you're running in 32-bit mode, the processor can actually emulate it, or in 16-bit mode. Actually, I need to go and check that. Is it 32-bit or just 16-bit? I think it's both, but anyway, it can emulate it. In 64-bit mode, however, it cannot. In fact, if you try to execute one of those instructions in 64-bit, if the emulation flag is set or if the task switch flag is set, it will raise an exception, and that's or a general error. So that's not good. So this is basically just saying you can't rely on floating point emulation. Don't rely on it. I don't know who would do that these days, but there you go. Right, so what we're going to do is we're just going to go through and check these things. When this code is called, this is a 64-bit UEFI executable. So when this code is called, we are running 64-bit code. We are using RAX, R8, whatever registers. We are running instructions with REX prefixes. We are full on 64-bit. So all the tests I'm going to show you here are kind of redundant, because this code wouldn't even run if it wasn't 64-bit long mode, which is the mode you need to be in to be able to execute this code. But that's not the point. It's a little exercise. It's always good to do these things when you're learning new things, when you're trying out new things. And it gave me an excuse to write some assembly code, even though it's AT&T syntax. I know, by the way, and thank you for that, from Andrew Kelly pointed out that there is going to be Intel syntax support. There's also there's a whole lot of work on a new inline assembly, I suppose you could call it a syntax/format for Zig, which looks really cool, really powerful. It's probably not quite ready yet, or at least I haven't seen it. It's not really that important. Let me do baby steps. I'm going to start with, a file of actual assembly instructions written in actual assembly. One other thing as well, by the way, which I need to mention, is that the memory model is flat, so selectors are set to be flat, which basically means that the global descriptor table, which lists all the different code and data segments at different privilege levels, it lists whether they're executable, whether they're present, what the page size is, where they begin and how big they are. They all start at 0. So every segment, CS, DS, ES, FS, GS, blah 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 blah, they all start at 0 and they all cover all the memory. And so there's no segmentation, and that's important. That's the modern way. That's what long mode in particular does. There's absolutely zero use of selectors for anything other than legacy, really, if you're running in compatibility mode. Okay, right. So on this side, I've got lots of code I'm calling to check whether things like is protected mode enabled, yada yada yada, and I've got the implementation in assembly over here. Now, I had to do a little bit of backwards bending to get this code into the build. Here I tried to get this adding assembly files to work with the build.zig. I still haven't been able to wrangle build.zig properly. I know it's in flux, so that's probably why, and it's probably also not helped by the fact that I don't really understand it yet. But so I have to do this separately. But just in case you run across this, it's perfectly fine to just build your assembly files, build object files from it using Zig Clang here, and then you build your Zig file and you just bring in the object file here, right? So I got it here. So it's not elegant, it's not wonderful, but it works. It's good that it works. And I'm sure it'll be absolutely fine. It's going to be something that will work in the not too distant future, even for me. Okay, so let's see what I'm doing here. So I've got my .s file, which has all the implemented calls to do the assembly instructions that I need. I've got my little wrapper around that, kernel.zig, which has some helpers that use some of these, export some of these. So for example, is protected mode enabled? This one here. Is this function here. It reads the control register 0 and it checks whether the first bit is set, and that's it. That means the protect enabled is set. I've kind of set a bit of a harsh halt here if it's not enabled. Again, it's sort of pointless because I couldn't even get here really realistically unless that was enabled. But there you go. Let's be prudent. Is paging enabled? Sort of similar thing. Also the CR0 register. Check the highest bit in this case. Returns true if the paging bit is set, which means that paging is enabled. We have page tables. Physical address extension. Remember that was a maybe enabled. So that was a hint, a suggestion. So I'm just checking it here. That's coming from CR4, control register 4. I've got these control register ones. I've used a macro. I felt quite proud that I managed to figure out how the macros worked in this syntax. It's not rocket science, obviously, but so I've got that expanded for CR4 and 3 and 0 because they are the most commonly used ones for the sort of for the things that we need here, which have to do with paging or page tables or other things. Right, and then there is the task switch flag, which is CR0 EM flag. So I'm testing for that. Oh, sorry, that was wrong. That's CR. No. I'm going back and forth. Here you go. CR0. That bit there. x86 emulation. That one there. Also CR0. So I'm testing those. Then I've implemented CPU ID. There might be one already in the lib standard library. I'm not too fussed about it. It's fine. It's good to implement it yourself. It's a good mental exercise. So that's the thing I've got here. That's the biggest one of these little guys. This was one that really tripped me up because I always get the order wrong because Intel and AT&T syntax are exactly opposite when it comes to source and destination. But anyway, this one does the trick. It sets the leaf and subleaf functions in RAX and RCX, calls CPU ID, and then it shovels the register values back into the whatever is pointed to by R8, which is a 32-bit array of 32-bit integers. I guess I could have set that. I tried to set that to a fixed number because it really only needs to be 4. But I couldn't quite get it to compile. I'm I'm sure I can though. It's just a matter of fiddling with it until I understand it properly. All right, so I do that and I get the max leaf. That's a typical thing to do. First thing you do is to call CPU. Well, actually, the first thing you do is to check is CPU ID even supported. It's not always supported, but I think the chances of you finding a processor, an Intel family processor, an AMD family processor that doesn't have CPU ID, then you must be running on very esoteric hardware indeed. So I get the max leaf, which is the maximum function that we can, the maximum function number, leaf number we can call on CPU ID or using CPU ID. There is higher numbers as well. For example, there are the hypervisor extensions, etc. But this is sort of the basic functionality. I read the E-flags. I was just going to do that because I was intending to do some more checks around, for example, this one here, whether is it actually clear. Of course it should be. Are the interrupts actually enabled? So it's the interrupt flag set. I just haven't written that code yet. The next thing here is to check whether or not long mode is available and is it enabled. So long mode is the 64-bit mode where we can access and run 64-bit instructions. We have the full instruction set, full register set, etc. That's long mode. Long mode has two sub modes, which are called, which is 32-bit compatibility mode and 16-bit compatibility mode. So you can run 32-bit code and 16-bit code even if you are in long mode. It's a whole family, a whole tree of different mode and permutations. And interestingly enough, it's kind of interesting that it's not really, there's not a single way. You can't just read a single value and say I'm in that mode. You have to check a few more modes. Although at this point, as I was saying earlier, the fact that we're running this code, which has been compiled to 64-bit code, is using 64-bit registers. Clearly, you know, we are in long mode. But should you want to figure it out, you have to call CPU ID with this leaf function here. And that will tell you whether, so by checking the third one of those, which is ECX, and checking bit 29, you find out whether or not long mode is available. Can this processor that you're running on actually even switch into long mode? And the next one is the extended feature register, which is one of the MSRs, the machine-specific registers that Intel has a whole sleuth of these things. This is a particular one which you read again. These things you find out which ones they are. They are all listed in the Intel developer manuals. I actually, on that note, I use both the Intel and the AMD 64 manuals. The Intel manual is, in some sense, the more formal one of the two, and it's enormously rich in information. But I think the AMD 64 one seems to have a bit more, I don't know, almost like it has a bit more sort of developer-focused information in cases, sort of things that you, okay, so I have the list. I have a list of all your opcodes. I have a list of all of these things and all the rules and the sort of the legal speech around the use of your architecture. Now, how do I actually use it? And the AMD manuals seem to be a little bit more towards the latter, which is good. So, but you need them both. Okay, so I check whether is it available, is it enabled, and then I say yes, it is. And then the last thing, again, completely redundant, however, a good exercise, is that I will go through each of the GDT, the global descriptor table entries, and I will look for executable ones because they are code segments. I will check if the long mode bit in that entry, the GDT entry, is that on? If it is, then I will check whether or not that particular selector, that particular GDT entry, is the selector of my current executing code segment. So what I've done then is I've basically found other executable code segments, and is there at least one of them that is the one we are running? Because at that point, I have absolutely convinced myself that I'm running in 64-bit long mode. In fact, this very code is running in 64-bit long mode. Totally redundant, but interesting. Okay, so what I did was I created this file here. So I've got this, in fact, here I'm referring to the AMD architecture programmer's manual up here, because it's such a good source, especially for this kind of information. The Intel one is quite terse here. It doesn't really give you a lot of, I found it a bit too dry. So this is basically, each of those entries are 64 bits, and this is how the bits are laid out. Love this syntax, by the way. I mean, I know you can do it with C, right? You could do bit fields in C. It's just, I just like the syntax. It's brilliant. So this is just laying it out. In long mode, most of these fields aren't really used. So things like the base, so basically where does the segment start, how big is it, they're not used. I think they could probably be filled in with anything you like. I think that there is a sort of tradition of what they're set to. So for example, base low here, or base will be set to 0. Limit will be set to FFFF, even though they're ignored. I don't know, I think it's just, it's sort of like, habit. And then there are some other important ones that are used. So for example, this one is used. So is the segment executable? That's the one we'll be checking for whether or not it's a code segment. It's a reserved one. Privilege level, that's important. Is it a privilege level? Most of the segments, in fact all of them, when you start up, are going to be set to privilege level 0. You only add more privilege levels when you start, when you're ready to switch to user mode. Which we're not going to do here. Present, fine, that's whether or not it's actually there, can be used. This is the one that's the interesting one. So that's the long mode bit, only in 64-bit, only if it's an executable segment. Otherwise, it's actually considered to be a reserved one and has to be 0. And this is one that actually encodes the size. This is granularity. This one isn't used for 64-bit either, by the way. Granularity is the size of the pages, also not really used for 64-bit because you can have megabytes and gigabyte pages in those modes. So what we do is we use this little function here to call into the assembly function, which is over here, and to store the GDT into that memory value. So it stores it into the GTT loaded, which is this this structure here, this packed structure here, which contains a limit and a base. So it's very similar to a GDT entry itself. It's basically an array of GDT entries, and limit gives you the amount of bytes that they take up, which is what you can use to determine how many they are. And that's what we do. So we load it, and then I slice it using this wonderful syntax, which is great. It's just brilliant. I can do that, right? I can take here's I don't know how many, but I can figure it out. And presto, look, I can return a slice. It's marvelous. So that's what I do. I return a slice, and then I iterate over it in this beautiful form. And I check each. Is it executable? Yes. Does it have an LM bit? Yes. Is the selector, so the selector will be the actual byte offset, so the segments, the code segment, the data segment, etc., they will be set to the byte offset inside of the GDT array of where the GDT entry starts. So I calculate the byte offset, which is the index times the size of the entry, and is it equal to that, yes or no? And I think it's like the 5th or something entry in this table. There's quite a few entries in this table. I don't list them. I did originally, of course, when I first wrote this, but there are quite a few entries. There are no hard and fast rules. The only rule is that the first one, so entry 0, is a null entry. It's always a null entry. That's the one that gives you the invalid pointer access, null pointer access trap, and that's the one. Everything else can be whatever it likes, and usually you'll have a kernel code segment, a kernel data segment, which is used by all the other ones as well. And they are, by the way, they are in the same memory space. They just have they're different types, right? So the code segment obviously is executable, and is read. Hang on, no, it is read, right? And the data segment is not executable, etc. And that's really it. And then at this point, we print out this saying, yep, we are indeed running in the 64-bit long mode enabled code segment, which of course we know we are, because otherwise we wouldn't even get here. Fine. So that's that. Now, I'm kind of excited because I just watched Andrew Kelly's presentation on memory allocation in Zig, and one of the things that I was going to do next was to set up memory allocation because obviously at this point the UEFI application is loaded. I can get a memory map, and I'll do that as part of that work, and I'll create a video of that as well. You can call into the system table here. It has some functionality for you to get hold of the memory map, so you can iterate over that. You can get information about the types of memory it is, etc. Some of that memory is used by the UEFI firmware, the bootloader itself, your own code, and then you can pick out the bits that are available for you to use. And there's lots of functionality around that, which is pretty cool. And then what I'll do is I'll take that memory, and then I'll basically attach arena allocators to it, to all the different contiguous blocks, and there you go. Now you have your heap effectively, right? That's how that works. So that's pretty straightforward. It's kind of cool with Zig that I can do that so easily, that it has that whole that's all built into it. The fact that Zig does not have a runtime per se, and the fact that this especially the allocators, that you have to take so much control of the allocators, and you are in a sense encouraged to do so for this kind of programming. And I would argue, for my background is games and consoles and things, I would argue for anything that is performance sensitive, or anything where you can run into a real nightmare if you fragment too much memory, particularly for performance. Games, for example, they need to be very careful about memory allocation. The rule in games programming is you do not allocate memory during runtime. You just don't. I know it's the same for other types of high performance programming as well. This idea that is built in, that the very idea is built in, that you should be conscious about how you allocate memory, I think that's really good. And so I'm very excited about doing that next. And hopefully I shall be able to do a recording that I can share with you all. So thanks for that. Bye.